Hey there, and welcome to this next lesson on higher level mathematics. So, you see, now we're moving on to a new topic, algebra, and today we're looking at the fundamentals. So, what algebra is, what we can use it for, and some basic techniques that we need to know and be familiar with in order to uh, do those things that we want to do. So, let's look at the lesson plan. So, just four parts today. What algebra is, what exactly it is, what its purpose, why should we care about it? Then we're looking at something what's known as linear equations. So we'll take a look at what it means for an equation to be linear and how we can use these to solve for unknown values, which is a key part of algebra. Then we're looking at linear inequalities. So equations when things are equal, inequalities being when they're unequal. How's that different from equations? What things we need to be aware of? And then what we're going to look at is applications to ratio. So, especially many of the harder questions, you might approach it, you might have at GCSE. Sometimes it's because it's using many, it's pulling on many different skills um, from your math knowledge. So it might be like ratios and algebra together. So and algebra is one of those topics that really can be inserted into many other topics quite easily. So we're going to see various scenarios like that. Today we're looking at just application to ratio because we've done that quite recently. So what is algebra? So algebra is a branch of mathematics where we represent unknown values as symbols, and we want to try and find those unknown values. So we're given information about these unknown values, and it allows us to form equations that we can then solve. So that's one of the key things we do in algebra, solving equations to, find these unknown values. And but what we also want to do is just study the relationships between various unknown values. So that's kind of like relating to that proportionality that we did before, seeing how things change as one thing changes, how does another change? Um, so let's look at just a general logic problem, which you might have heard of before. So it's like it kind of goes like this, where I say I'm thinking of a number and I multiply that number by three, I subtract five from that value, and the result is equal to seven. And I ask you, what is the number I was thinking of at the start? So logically, a lot of people would understand. It's like, oh, you need to start with that end value of seven and gradually work your way backwards. So we had a value of seven. I subtracted five, so therefore you need to add five to get 12. I multiplied the number by three, so you'd have to then divide by three, and you'd get the answer of four. And there you go. That would be the answer. And that is basically algebra there. We, but algebra, we're essentially formalizing that process, being able to write it down into symbols. So then we can then solve more complicated problems because this is a relatively simple one. So yeah, we have my unknown value, we represent it like x, and then we're doing a series of operations to that unknown x. We're multiplying it by three, subtract five, and we get seven. And so, yeah, if you want to work your way back, you do the opposite set of operations: add five, divide by three, and the order of those operations is important. Um, so you're not only just doing the reverse operations, but you're doing them in the reverse order as well. And you see, yeah, that seven will come back to four. So how do we formalize that like an equation? This is an example of a linear equation. Linear meaning it's an equation that just we don't have our unknown to any kind of powers or roots or anything like that. So we don't have that in this case. We have our unknown x, and I multiplied it by three. Now, three directly next to an unknown value like that implies multiplication. So we've got three times x here, and then we subtract five, and the answer was seven. So that problem we just looked at would be equivalent to solving this equation. And how we solve this equation would be very much in the same way. And how, how we do it is by manipulating each side of the equation. And I like to think of it like these old-fashioned weighing scales, where you put a weight in each side, or in this case, we're looking at a calculation. 6 times 4 on the left, 14 plus 10 on the right. You see they both come out to the same value. And so the scales are in balance. But say if I add 5 to the right-hand side, you see it then tips down. because that side is now heavier or the number is bigger, unless we added 5 to the other side as well, and then it stays equal. And so that's the important thing when it comes to solving equations. By making these series of manipulations, as long as we do the same thing to both sides, we're fine. And we have more options now than say we've already done a similar thing, haven't we, with fractions and ratios, like the top and bottom of a fraction or each side of a ratio. You can multiply or divide both sides by the same number, and it doesn't change it. Well, those were dealing more with like relative amounts, whereas here we're dealing with an actual equation. Like, no, this value is equal to this value. And so we don't just multiply or divide. We can add or subtract or even, take powers of both sides. And as long as we do the same thing to both sides, it's going to stay equal. And that's how we then need to solve this equation. So what we need to do, we need to get rid of that -5. So what we do is we add 5. But as long as we add 5 to the other side, it stays equal. So we get 3x equals 12. The -5 and +5 cancel out, the 7 and the 5 add to get 12. And now we've got 3 lots of x is 12, but we want just one lot of x. So what we do is we divide by 3. And again, if we divide both sides by 3, we get x equals 4. So you might prefer like what we did a moment ago, just the logical side of it, just thinking of it logically rather than, this formal process of, manipulating both sides of the equation in a way where we can then get x by itself. So it's then x equals 4. But we need to be confident with this because then as you then move on to more complicated equations, you won't be able to just do it logically by thinking in your head. It'd just be impossible. And so that's the whole point of algebra and these manipulations that we do to then solve an equation. So an example like a real world example of this equation, for example, is say if you have this, you're trying to calculate how much data you used on your mobile phone network. Now, this is the example I've got here. And your provider charges £3 per gigabyte, but you already started the month with £5 of credit. After that end of that month, you receive a bill of £7. How much data have you used? That would be a scenario that would be modeled by this equation because you think about it. The amount of data we've used is our unknown x. That's what we're trying to find. But we know it charges £3 per unit of data. So 3x is going to be how much we've spent. But we already had £5 of credit. And, so there's £5 we're not going to be paying for because we already have that credit. So the total bill is going to be 3x minus 5. And we've been told that came to £7. And so you see this 3x minus 5 would model this scenario. And if we then solve that equation, it gives us x equals 4. So that would tell us we used 4 gigabytes if this was the scenario we were faced with. So that's an example of algebra being used to solve a real life problem. So now we need to learn kind of more some general techniques that will help us in solving equations, like one of them being collecting like terms. So when you've got something like this, and a term of equation is these. So it's a number with a sign in front of it, and perhaps our unknown. So you've got things like 2x, you've got -2, you've got plus 7x, and so on. And so these terms we can move around any way we like as long as you move the whole thing. The main thing being wary of is that sign in front of the your number is part of the term and has to come with it. That's a mistake I often see. So say if I want to bring all the x's together, the x terms, you see here I've got a 7x, I've got a 2x, and I've got a -3x. And with the number terms on that left-hand side of the equation at least, we've got 5 and we've got -2. And you see the minus comes with the -2. The minus sign comes with the -3x. Don't forget that. And that 2x at the front, even though you don't see it at the start, it's essentially a plus 2x. And so that's why you see that plus appear there. And so then we can just bring them all together because 7 plus 2 minus 3 is 6. We've basically got 7 lots of x plus 2 lots of x minus 3 lots of x. And so all that together comes up to 6 lots of x. Like we don't know what the x is, but we know we're going to have 6 lots of it. And then 5 minus 2 is just simply 3. And so now we have an equation very similar to what we had before. And so we can do the same things we've done before. But first, we can actually simplify this a little bit because you notice each of those numbers has a common factor of 3. So we can divide everything through by 3, divide both sides of the equation by 3. So it'll stay equal because we've done the same thing to both sides. And so 6 becomes 2, 3 becomes 1, 15 becomes 5. And now we can solve it the same way we've done before. Subtract 1 from both sides. Now divide by 2. We'll get x equals 2. Now, what do we do when we've got the unknowns on both sides of the equations? Say something like this. Like we can't just easily collect the like terms like we did before because they're on opposite sides of the equation. What we do in this case, we just essentially need to subtract, or I should say remove our x term from one of the sides. So in this case, we could subtract 3x from both sides. And I say remove, not subtract, because it's 3x in this case. So we minus 3x is going to then remove it. It's going to cancel it out. But if it was minus 3x, then we would have to add 3x in order to cancel it out. So you basically got to just do the opposite. Because now we see the minus 3x, no, the 3x minus 3x on the right hand side is going to cancel out and leave us with just the plus 3. And on the left-hand side, we get 5x minus 3x gets 2x, and then you've still got the minus 13 just sitting there. And again, now we've reduced it to a scenario that we're already very familiar with. So we can add 13 to both sides to get the numbers over on one side and the x term on the other. And we've got 2x is 16, so half it, we'll get 1 lot of x, which is 8. So you see, this is the importance with not just algebra, a lot of maths in general, really. And I always encourage you to make sure you understand each part before we move on because you see how it kind of builds upon each other. And so if there's one thing you don't understand, then the later thing will be, kind of inaccessible. Right. So how do we deal with something like this? So we're times by numbers. Now let's look at if we're dividing by numbers. And well, when we're just dividing by a number here, like there's no x term on the denominator or anything like that, we can just multiply the numbers out. So on the left-hand side, if we multiply by 8, so we'd have to multiply both sides by 8. That will cancel out the fraction, like the denominator of the fraction on the left-hand side. And if we multiply both sides by 6, that will cancel out the denominator on the right-hand side. So we could end up multiplying both sides by 6 and 8, but that actually makes a bit more work for ourselves because we're multiplying by an unnecessarily large number. What we want to do is instead look for the lowest common multiple of 8 and 6. So we want a number that is basically a multiple of 8 and 6, but we want the smallest one possible, and that's the lowest common multiple, isn't it? Which we've already done. And for these small numbers, you probably won't really take much working out. You'd probably be able to see it that 24 is the smallest number that is a multiple of both 8 and 6. So on that, so we multiply both sides by 24. So we know the result will still be equal because we're doing the same thing to both sides. But on the left-hand side, we could see it as multiplying by 8 and multiplying by 3, which makes 24, doesn't it? But multiplying by 8 cancels out the denominator, and then multiplying by 3, the 7 becomes 21, the minus x becomes minus 3x. On the right-hand side, we could see that 24 as multiplying by 6 and multiplying by 4. And so the multiplying by 6 just cancels out the denominator. Multiplying by 4, then the x turns into 4x. And so now we've got something very similar to what we have on the left there. So we could just add 3x to both sides. So we get 21 equals 7x. Now divide both sides by 7, we get x equals 3. And you see I've just kind of flipped it around there. Rather than having 3 equals x, we just swap it around to be x equals 3. Cool. And you can easily do that with any equation. You can just swap the left and right hand side around. As long as you swap like the entire sides around, like you can't like pick and choose terms or anything like that. So that's how we deal with that. So now let's look at a quick look at multiple unknowns. We're going to come back to this in a later lesson in more detail. So something like this, where you see we've got x and y, two unknown values, different unknown values. Well, first things first, we can collect like terms just like the same way we've done before. So you see on that left-hand side, we've got a 5x and a minus 2x will come together to be plus 3x. On the right-hand side, we've got a y and we've got a minus 4y, which comes together to make minus 3y. And everything else just stays the same. So we've got 3x minus y plus 3 equals x minus 3y plus 13. Now, what we could do is get the x's and y's to one side like this. So what I've done is I've subtract x and add 3y to both sides. So it cancels out the x and the minus 3y on the right hand side. So on the left hand side, we've got 3x plus x, 3x minus x, sorry, gets 2x. And minus y plus 3y gets us positive 2y. And, numbers stay the same. And now we can kind of do some basic manipulations that we've already seen before, like if we subtract 3 from both sides. Here you see there's a common factor of 2, so if we divide everything through by 2, we get x plus y equals 5. And that's as far as we can go with these. When you've got two unknowns, really, to get an exact solution, you need two or more equations. With just one equation like this, you're just going to get a whole multitude of solutions. Like, say here, x and y, all these would be solutions to this equation because x equals 1, y equals 4. Well, 1 plus 4 is 5. 2 plus 3 is 5. 7 plus minus 2 is 5. So these are all solutions to the equation because if you put in those x and y values, it produces 5. Whereas you could get a whole bunch of other values like this that aren't solutions. So 5 plus 2 is not 5. 6 plus 0 is not 5, and so on. So it's not like anything goes, like any values of x and y are possible, but we do get many solutions. And if we want an exact solution, we'd need another equation. At the moment, all we could do, like say if we wanted to subtract x from both sides, we'll get y equals 5 minus x. If we subtract y from both sides, we get x equals 5 minus y. So we can only ever get one equation in terms of the other equation. Sorry, we can only get one unknown in terms of the other unknown. You can't get an exact numerical value for either one of them with just this information. So we need another equation, typically is the other information we need. And we solve them simultaneously. That's what's known as simultaneous equations. We're not going to be looking at that for a few more lessons yet, though. So that's linear equations. So we're solving, these basic equations, linear equations. So that means no powers of x. We ain't got x squared or x cubed or anything like that. It's just x or y squared or y cubed, whatever your unknown is labeled. It doesn't matter. We typically label it x, but it could be anything. Now we're looking at inequalities. So that's basically dealing with greater than or less than scenarios. So say if we look at it just in terms of numbers first. So we've got 9 is greater than 4, obviously. So, but let's see what happens when we start to manipulate both sides of these like we would with an equation. Like, so I've drawn a little number line here. So imagine like the 4 is the red, the smaller number, and then 9 is the green. It's the larger number, more to the right. And now imagine I've added 3 to both sides. So you see, with this numerical example, you can, 12 is greater than 7, which we know is true. But we can visualize it on that number line. Like adding 3 is essentially like shifting both to the right by some constant amount. And so if the green is greater than the green will stay greater than the red because they're both shifting along by the same amount. So that makes sense. The sign is not going to change there. It'll stay greater than. Likewise, if we multiply by a positive 5, you see 9 becomes 45, 4 becomes 20. We can see, yeah, 45 is greater than 20. But in the more general sense, with our two arrows there, if we're multiplying by 5, it's like scaling it up. So they're both increasing, but they're increasing by different amounts. Like the bigger number is going to increase by more. And so the gap between them gets bigger. But the main thing is the green one is still bigger. So you see that's not going to change the sign either. The green one stays bigger. Now, if we take a scenario like this, like say when up times by minus 2, you see what happens? Like the 9 becomes minus 18, the 4 becomes minus 8. And minus 18 is less than minus 8 because it's more negative. And it's not because we multiply by 2. That's fine. With multiplying by any positive number is fine. It's because we've multiplied by a negative number. And you think about when you multiply by a negative number, say positive 5 would become negative 5 and negative 10 would become positive 10. So it's like everything has been flipped upside down. So looking at our number line, it would essentially be doing this. We'll just flip the whole thing upside down. That's essentially like multiplying by a negative number. And now you see that does have the result of the green now being the smaller number. It's more to the left. And so That's why multiplying by a minus sign, a minus number, or dividing by a negative number as well, will cause the sign to flip. So you see, we had greater than, greater than, greater than. Now it's less than. And another example, which you might not come across so often, but it also has the same effect, is the reciprocal, which makes sense. If 9 is greater than 4, then if you divide by 9 and divide by 4, you're now dividing by a bigger number, so the actual fraction will become smaller. So flipping each side of the equation. We'll come across that later, but that's another thing that will affect the sign of the inequality. And as a little aside, quickly, because you won't really come across this much, is what happens when you square both sides? Like with the 9 and the 4, you see it's fine. If we square both sides, if we square root both sides, the sign stays the same. But that's not always the case. It depends on the numbers. So say if we have something like this, if we square both sides, that minus 9 becomes positive 81, which is bigger than 16. And so you see the sign does flip there. And so that becomes a problem when we're dealing with algebraic inequalities. So if we have x is less than 5, if we square both sides and we have x squared and 5 squared, which is 25, is x squared now less than 25 or is it greater than 25? And the answer is we can't know because it depends on the value of x. If x is less than 5, well, let's say x was 3, then 3 squared would be 9, which would be less than 25. However, say if x was minus 6, and minus 6 is less than 5, if we square minus 6, it becomes positive 36, which is greater than 25. And so it all depends on the value of x. It could be less than, it could be greater than. And so we just don't know. So like I said, you won't really account for these very much, if perhaps at all. But it's just something to be mindful of. You might want to play around with, squaring and square roots and see how it affects things. So let's take a quick example here. So this one's quite a simple example because we can just solve this in very much the same way we've done with regular equations. So we add 12 to both sides, we get this, and then we divide both sides by 7, and we get this. And you see that sign never changes because the operations we're doing, plus 12, divide by 7, they don't change the sign at all. But you might get scenarios like this where it will. So say it all depends how you calculate as well, because sometimes there's multiple ways to calculate uh, the solution to an inequality. Some, one maybe that does cause it to flip, other ones where it might not cause it to flip. In this case, let's say if I was to subtract 28 from both sides and I get this, and now I divide by minus 4 and I get this. You see the sign flips. And you see that sign there. This is something to be aware of as well. So this is not greater than, it's greater than or equal to. That's what that little line underneath means. It's like half an equal sign, isn't it? So you got to be wary of that because that can play a significant role in certain questions. Is something like less than or greater than, like strictly less than or greater than, or is it less than or equal to? It can be like less than, but also equal to that value. So that's what that essentially means. So now on that right hand side of the equation, if we finish up this solution, we've got minus 28 divided by minus 4, x is less than 7 because the two minuses cancel out, don't they? So we get 28 over 4, 7. Or you can have a scenario like this. We could subtract x from both sides, which is fine. And we get this, even though we don't know what x is, it's fine because we know subtraction doesn't affect the sign at all. And so we can then continue this if we subtract 1 from both sides, and now we divide by 5. It doesn't flip the sign, although it might look like the sign is flipped there, but that's because I've flipped the entire thing around, because we would have got 2 is greater than x. But typically we tend to keep the x on the left-hand side. So what we do is flip the entire inequality around, and so we get x is less than 2, which is essentially the same thing as 2 being greater than x. So it's not causing the sign to actually change, we're just flipping the whole thing around. So a few little things to be mindful of there. We can add or subtract by x. You just got to be mindful of you can't multiply or divide by x unless you know that x is positive. Because imagine if I multiply both sides by x, I don't know what x is, and if x is positive, it won't cause the sign to change. But if x is negative, it will cause it to change. So you've got to be wary of that. But adding or subtracting x is perfectly fine. Right. So last thing, let's just look at application of ratio of algebra to ratios. So you might get an example like this, where we've got two unknown quantities in a ratio to one another, and we know that we've been told that this ratio is a 2 to 9 ratio, and we need to use that to work out what the value of x is going to be. So this can be quite a tricky question because a ratio in general, students can find quite tricky, but when you add in some algebra as well, it can make it very tricky. So let's break this down. So well, first of all, we can just try a bunch of different values for x. So if we put x into either side of this ratio, you get 3 to 0, 4 to 3, 5 to 6 for different values of x. And some of those ratios can be simplified like this. And you've got the top one is actually undefined. It's not a possible solution at all. Like you can't have something like a ratio with a 0 in it because it's essentially like like in a fraction, it's like dividing by 0. You just can't do that. It just doesn't make sense. So you see, we've got a bunch of solutions here. None of them will come to 2 to 9, but that's essentially what we're looking for. We're trying to find the value of x such that this ratio will be 2 to 9. And how we can do that is by trying to calculate what one part of this ratio is. So you remember we have the full ratio. It's like breaking something up into 11 parts because 2 plus 9 is 11. And it's like 2 parts is going to the first and 9 parts is going to the second. So that x plus 2 represents 2 parts. And that 3x minus 3 represents 9 parts. And so if we do x plus 2 divided by 2 and 3x minus 3 divided by 9, they're both going to represent 1 part. And now we can set them equal to one another because we don't know what that part equals, but we know they both represent that 1 part now when we do that division. And so we know they're both the same value. We can set that equal. Now we have an equation we can solve. And we know we can solve this. We've already done something like this earlier on. So first of all, we can simplify that one on the right because there was a common factor of 3, 3x minus 3 on the top and 9 on the bottom. Divide, the top and bottom by 3. Same rules of fractions apply. Now, what we need to do is multiply out those two numbers. Here you see 2 and 3. There are no common factors. So the lowest common multiple is just simply going to be 2 times 3. And what we can do here is essentially do what's known as a cross multiplication, which will be handy later when we're dealing with situations where we do have an unknown like x on the bottom, on the denominator. And a cross multiplication looks like this, where we take the x plus 2 and times that by 3, and the x minus 1, we times that by 2, and we'll get this. And the reason why we can do that, because what we're doing is we're essentially just multiplying both sides by 6, which is 2 times 3. But on the left-hand side, what's end up happening is the 2 cancels out with the denominator, and then we multiply the top by 3. On the right-hand side, the 3 cancels out with the denominator, and the top's getting multiplied by 2. And so it has this effect of what's known as a cross multiplication, because you see these arrows are crossing one another. You can times each numerator by the denominator on the opposite side, and it essentially cancels out those denominators. And so that's a handy technique to have, especially like I was saying, when we come to a point where we're dealing with x's on the denominator. So cross multiplication. You want to make sure you're familiar with that. Now we've got this that we know how to solve. Like we can subtract 2x from both sides to get x plus 6 is equal to minus 2. And then simply subtract 6 from both sides. We get x equals minus 8. So there you go. That's how we would solve a problem like that. So you're using your knowledge of ratio. Like don't let the x throw you off. Like the x is just a number. We don't know what the number is, but it's just a number. And so you just use your knowledge of ratios in the same way to produce an equation. This is what we're always trying to do, like with algebra. We have some unknown and we have some information about that unknown. And what we want to do is use that information to form an equation. And then we use our techniques that we've developed in solving equations to then find the unknown. That is like the premise for so many different types of problems. If you can just understand that sort of logic, then it'll serve you well. So that's it. That's the fundamentals of algebra. So we're going to move on to more advanced stuff next time. So did you know algebra actually is one of the oldest fields of mathematics? It didn't even reach European countries like the UK until relatively recently. So it actually dates back like over 4,000 years, coming from ancient Babylon. The actual word algebra itself comes from the Arabic word known as algebra, which is which translates as the reunion of broken parts. So we have algebra is all about trying to solve unknowns, isn't it? And that unknown is seen as like the broken part in an equation, and we're trying to find out what that is and reunite it with the other numbers. So that's where that comes from. We in the UK say we only really learned about it about 800 years ago, which is relatively recently, compared to 4,000 years when Arabic texts were first translated. And it's also where we got our number system with like numbers 0 to 9 and place value, how we use that to create bigger numbers from those initial 10 numbers. Uh, and the number zero itself, like we didn't have a number zero. We were still using Roman numerals back then, which is not very good for mathematics at all. Like Arabic numerals are so much better. So yeah, that's where some interesting facts about where algebra comes from. Right. So like I said, we're moving on next time to nonlinear equations. So we've only looked at linear so far, which are kind of like your simplest equation. We're going to take it up a notch next time. So I'll see you there. But of course, the takeaways here for you. Make sure you hit all those the checklist and you understand like all these fundamentals before we build upon them. But I'll see you in the next lesson.